Okay, good afternoon, everyone. Welcome to this theme session organized by the Lectorenplatform Biobased Economy. My name is Jarno de Witte, and I'm the chair of the Lectorenplatform. And it's good to see so many people are joining this afternoon. This afternoon we have a webinar about recycling of bioplastics. And see if I can go to the next slide. So this afternoon, this is our program. So first I'll have a brief introduction. Then we go to a presentation by André Heeres. He is lecturer at Biobased Chemistry and Refinery at Hanze University of Applied Sciences. And he will be talking about downstream processing of sustainable aromatics towards bioplastics. Then we have a second presentation by Jarno de Witte. He is a researcher at Biobased Chemistry and Refinery, also at Hanze University, and he will be talking about upcycling of PET waste through selective ammonolysis. And then finally, we have a presentation by Chenyu Zhou, who researcher in my research group, Biobased Resource and Energy, who will be talking about AI-enhanced prediction of plastic pyrolysis. And then at the end, we have about 15 minutes left for questions and answers. So that also leads me to the question, if you have any questions about the presentations, please put them in the chat. I will be carefully looking at them. So in the end, I will be able to ask the questions to the different speakers. And of course, the presentation will be shared afterwards. So you can always have a look at what's being told today. Well, to first start with a very brief introduction of the Lectorenplatform Biobased Economy for people who do not know it yet. So the Lectorenplatform is a collaboration of lectors from 14 different universities of applied sciences in the Netherlands, and you can see an overview over here of all the people who are being involved. And we already exist for quite a long time, and I'm happy to mention that we just got granted another 3 years of our Lectorenplatform, so we can continue with our activities. And the main goal of this platform is to stimulate innovation, adoption, and knowledge sharing regarding bio-based chemicals, materials, and energy. And when you look at the specific goals of the coming 3 years, we will focus on knowledge sharing and strengthening by organizing these thematic sessions. We also have our yearly platform conference, which will be on the 12th of November in the north of the Netherlands this time, but more about that a bit later, about publication of articles and also participation in the DAS conference. We further would like to expand our network in the coming years, so also to link with Tractoraten from vocational education, and with the Nationaal Groeifonds Biobased Circular, and with Green Molecules Collective. We would like also to evaluate a bit our focus of the platform, about the different themes we are focusing on, and exploration for establishing thematic networks. And finally, we will have our focus on further internationalization, especially in cooperating together in international project proposals towards Horizon Europe. So this is about a bit about the Lectorenplatform, and if you would like to know more, please visit our webpage where you can find much more information. So this is a QR code with the link to the information about the Lectorenplatform. Well, this is a bit about the introduction, because for me the most important is the speakers of today, and then I would like that's also already mentioned. So we have a conference on the 12th of November at the Energy Barn in Groningen. So already put this in your agenda. We plan to have a first preliminary program available beginning of next month. So we will send you more information about that. And then I would like to give the word to our first speaker. Then let me first stop sharing. So the first speaker of today is André, and he will be talking about downstream processing of sustainable aromatics towards bioplastics. So I would like to give the word to you, André. You're muted at the moment, so.
Yeah, so I will give my presentation together with Jarno. So I will start in, I think I actually need about 10, slightly less than 15 minutes, and thereafter Jarno will take the floor. Hopefully the slides arrive. Yep. Yes, so we'll make it full screen. It's clear? Yeah. Okay. So I will be talking about the downstream processing of sustainable aromatics towards, between brackets, bioplastics or plastics. Now, like Jaap already mentioned, so I'm working at the Hanze. At the Hanze, we have several expertise center. One of them is expertise biobased economy, different lectorates, and mine is based upon bio-based chemistry and refinery. Working in close collaboration with Janneke. We'll come back on that later on. Also having a hybrid research group together with the University of Groningen based on renewable carbon as a theme. And yeah, quite a large network of regional companies and consortia, but also with for example, large companies from Germany, BASF, Ludwigshafen, so it's quite broad. And as you can see, we also have quite a large team, approximately 15 people, senior scientists, 2 PhDs, though Johanna made a PhD last week. Also, what is nice, 6, 7 people combining research with education, so in Dutch, docentonderzoekers, but also full-time researchers. So that's giving a good mix, but also a nice bridge between research and education. Now, the theme of our group, so it's based on renewable carbon. And on the left side, you see a picture which is giving the boundaries of our Earth, and it's from the Stockholm Resilience Center. So actually, you can see that we are exceeding a lot of boundaries currently. Climate change is well known. On the right side above, you see also novel entities. You could think about things like molecules like PFAS, also pesticides, which we use often in agriculture, drugs which are released in the toilets. Well, and the last example is on below, you see the biochemical flows, which we are negatively influencing, for example, the phosphorus and the nitrogen flows. On the right side, you see a famous slide of the NOVA Institute based on renewable carbon. Renewable carbon stands, to be honest, for a material, plastics, amongst others. And you see that currently, most of you know that we currently make them often out of fossils. We should stop that. Instead of that, we should use renewable sources. And actually, what you see in this picture are 3 different sources: biomass, residues from agricultural sector, woody materials, end-of-life plastics, which is being depicted as recycling, and also a new kid on the block, carbon dioxide. So there's a lot of development on the low TRL levels, most often combining carbon dioxide with hydrogen, and via syngas you can go to a lot of other basic chemicals for the industry. Also, what I would like to know is also there's a lot of activity in fermentation. So carbon dioxide can also be converted by algae, other microorganisms to carbon-containing compounds, which can be used in order to make our materials. Now, ultimately, what is the holy grail? And that is depicted on the left side. So in principle, we would like to recycle as good as possible. However, in all the phases, production, use, end of life, and recycling, you have, of course, loss of material. And that is where bio-based renewable comes in. So these losses in this recyclable, of this renewable carbon cycle should be filled in preferably by bio-based materials, carbon dioxide. And of course, we would like to achieve a high rate of recycling as possible. To come back to my topic, this also counts for aromatic containing plastics like PET, and several polyurethanes are containing an aromatic unit in that. And approximately 40% of the plastics we currently use contain aromatics. Now, lots of different methods of recycling. So on the left side above, you see mechanical recycling, but sometimes the quality of the material is getting too worse. And then you can also go to chemical recycling, and you see a lot of different methods in this slide. A dissolution in which you retain the molecular weight of the polymer, but also going from using this recycling to depolymerize to monomers, purify them thereafter, and for example, repolymerize that. But you can also think about chemical recycling, going to naphtha, syngas, and you can of course burn the material and ending up in carbon dioxide. But the focus on my presentation will be about catalytic pyrolysis. And actually what we have developed in the last years, especially the company BioBTX has done a lot in that, is an ex situ catalytic pyrolysis. And I will try to explain this in this slide. So actually on the right side, you see there are two reactors. And in the first reactor, under an inert atmosphere, so nitrogen, we heat up biomass or end-of-life plastics till temperatures, till let's say about 500, 600 degrees. So under these conditions, you get degradation of the material. You get a vaporous phase consisting of olefins, alkanes, and if you use biomass, also aldehyde, small carboxylic acid. And that is transported by a nitrogen flow to the second reactor. And there is a specific zeolite catalyst, which is converting this vaporous phase into aromats. So the trick is that we have separated the pyrolysis part from the vapor upgrading part. And the reason for that is that in this case, you protect your catalyst from all kinds of contaminants which are present in your feedstock. So that was the main advantage of an ex situ catalytic pyrolysis, and that is currently which a company like BioBTX is still aiming for. Now, like I mentioned, so biomass or plastics converted by catalytic pyrolysis, and that results in approximately three sources, let me call it that way. So you have the aromatics, the aim of the project, the aim of the catalytic pyrolysis. You have char, which can be used as an energy source, and you have olefins and others, so a gaseous phase which can be recycled towards the feedstock. Now, these aromatics are being distilled, and you can rather easily isolate the BTX fraction from the higher aromatics. And if you do it properly, you can also separate the BTX fraction in benzene, xylenes, and toluene. And keep in mind that xylenes is a mixture of three compounds, the ortho, meta, and the para. The para-xylene can be obtained by distillation and crystallization. Now, what was, of course, the aromatics which are being produced by catalytic pyrolysis? Doesn't matter if you use biomass or end-of-life plastics, they are exactly the same as the aromatics which can be obtained from petrochemical sources. So it's a drop-in chemical. So you can easily say, well, this is the same chemical structure, so the downstream chemistry should also be the same. But of course, you should be aware of the fact that for a polymerization to high molecular weight, you really need very pure monomers in order to achieve such a polymerization. So the purity of these monomers should always be in the range of above 99.5%. And that was, of course, the question we had. So different feedstocks being used for the production of aromatics, does it contain contaminants which negatively influence the polymerization? So that is why we did, and I will show two examples, the downstream processes to PET. So what you see in this slide is end-of-life polyolefins, and the structure is not as nice as you see here. Catalytic pyrolysis, isolation of para-xylene out of this mixture of aromatics by distillation and crystallization. Then you do an oxidation of the para-xylene to terephthalic acid, convert that to the dimethyl ester, and then you have the monomer which can be used in order to make the PET. So a reaction of this DMT, so the dimethyl ester of terephthalic acid, with ethylene glycol obtained from bioethanol gives you the PET. And you see a picture of the PET which is being prepared by NHL Standard, but actually we analyzed it properly, and the physical and also other applications are identical towards the PET which is being prepared from fossils. So this is really a nice example that indeed you can replace fossils by end-of-life plastics, and we also did this for biomass. Now, the last example I would like to show is can we also convert this mixture of aromatics to twaron? And twaron is depicted on the right side. Jarno will also give some information about twaron, but it's a very strong fiber being used in ballistics tires. But actually that is being prepared from two aromatic containing monomers. And you see that on the right side below, you see two molecules. One is TDC, which is the diacid chloride of terephthalic acid, and you see PPD, paraphenylene diamine. So if you react that together, you get a twaron being formed. Now, how can you prepare these monomers? So in this case, we separated the benzene and converted that by a nitration reduction to aniline, deazotation, and then it ended up after hydrogenation to PPD. So this was the first monomer. Also, we're able to achieve the quality, the purity, which is being required by Teijin in order to do this polymerization, because the polymerization part was being done by the company Teijin. If you look at the other monomer, TDC, paraxylene chlorinated, and then the reaction of hexachloroxylene with terephthalic acid ends up with the second monomer. So actually we transferred this to Teijin, and they were able to make this twaron polymer, and also in this case the quality of the polymer was identical as being prepared from fossils. So to come to my conclusion, catalytic pyrolysis has the potential to convert end-of-life plastics, but also biomass, keep that in mind, into aromatics. And the downstream processes is processing of aromatics obtained and conversion towards high-value polymers like PET and twaron results in polymers with identical properties as fossil-based analytes. So this really shows that we are able to replace polymers currently being prepared from fossils also with sustainable monomers as an alternative. Thank you for your attention. I would like to give the floor to my PhD student and colleague Jarno.
Yeah, welcome everybody. Thank you, André.
Hey.
Well, as André already said, I'm a PhD student in his group, and I would like to continue this lecture with an example of what I've been doing my research on, which is actually the upcycling of PET waste through selective ammonolysis. Like, could we make out of this PET waste something nice, new material? So first, well, I think everybody will be familiar with PET. You see the structure of PET on the left, and mostly well known for the PET bottles, but also PET trays, which we come back to later. These are like the plastic trays you buy your meat in at the supermarket. So we want to upcycle this to twaron, and on the right side see the structure of twaron, and this is mostly used in ballistics, as André already mentioned, also like in fireproof firefighter suits and things like that. So we're going from a relatively cheap material to a very expensive, durable one. We did this in this whole project in the INREP project, in which you collaborated with quite a few companies, but mainly in this project we worked together with NTCP and Teijin. NTCP was the one who gave us the materials to start with, and Teijin and made the twaron in the end. So how do you do this now? Well, here you have the structure from PET, and both monomers for twaron you can make out of PET through two different approaches. The first one will be a hydrolysis of PET, where you enter with terephthalic acid, and then after chlorination you enter with TDC. These reactions are already more well known, but the top route is a more novel way to upcycle PET waste. And here we do an ammonolysis towards the terephthalic diamides, followed by Hofmann rearrangement with chlorine and sodium hydroxide, enter with PPD. And well, we send these two to Teijin and they will end up with Twaron. So now you think PET, that's nice, but what is the PET waste and the PET trace that we now actually used in this whole reaction? Well, this is like the sample we put into the reactor, but firstly we identified it on item based, and you see that mostly PET trace, some PET bottles, but also some other things. And if you look further into this on the polymer level, you see 87% PET and a little bit of polyethylene. That's because the PET trays are not just PET, they're bilayer plastic with polyethylene and other polyolefins. You can also see some cellulose in here, which is mainly from stickers and other organic components in the waste stream. So how can you now use this waste stream to end up with something really nice? We did this with ammonolysis in this kind of reactor. You just put in the waste stream itself, put in ammonia, ethylene glycol, heat it up to 100 degrees for several hours, and then we end up with terephthalamide in 75 to 80% or sometimes even higher yields. But the trick here is in how do you purify this whole mixture. Well, during ammonolysis, only the PET will break down into terephthalamide and we will free up the ethylene glycol from it. But the polyolefins and other some metals and cellulose, they don't react in this setup. So they will end up as like bigger fractions, while the TDA crystallizes out as very small crystals. So you get a suspension with different size materials. And this you can separate through a particle size separation method. Mainly just use some sieves to first filter out the larger plastics and metals and everything. And after that you filtrate the suspension you obtain to a little filter, and then you end up with terephthalamide, which already is NMR pure. Well, this terephthalamide you can, with a Hoffman rearrangement, convert into PPD, as we did through the scheme I already showed you before. Loes did really nice work in here to, is a colleague of us, to make a two-step procedure to first isolate the chlorinated terephthalamide, and then do the Hoffman rearrangement itself with just sodium hydroxide and water, and ended up with very pure PPD, which we sent to Teijin Aramid. Similarly, another colleague of us made the terephthalyl chloride through a similar method and purified it, the terephthalic acid through methylation and crystallization, and then demethylated again. And then with thionyl chloride, he converted to terephthalyl chloride. And we also sent this to Teijin. Teijin analyzed it with their analysis and showed that both monomers had the same purities as they normally gain from fossil sources. So then the 100 grams of both materials that we sent, they put in a reactor to polymerize this material towards Twaron, and then they spun it. Here you can see a little bit of the fiber that they made out of the Twaron from this PET waste. And they ended up with 1400 meters of yarn with the polymer strength that is equal to normal fossil-phase Twaron. So they really show that we can make this type of material from waste streams. Now you can also see that in some other pictures. This is what the Twaron first looked like after the polymerization of PPD and DDC. Then this is after they have spun it, and we made a little showcase from this material. This is called a tensegrity table. Basically, all the weight of the top table part and the waste stream that we use for it is hanging on a really tiny little fiber here in the middle, which this bike combined is like 3 kilograms. So you can really see that this little fiber really holds a lot of weight. So it's really strong. Now you might think, well, okay, this is really nice, but is this also economically viable? We did we analyzed this in collaboration with the university, with Jos Winkelman and Pascal Wessel, was a student of his. And they made this really nice scheme in Aspen and calculated how much the terephthalamide would be if you made it through this process. Here they set the PET stream, because it waste, they put it to as €0, there's no value yet. If you calculate it like that, you will end up with TDA, which is cost like €1,400 per ton. It's not yet fully optimized, so it can be a bit lower. But for comparison, we calculated quickly how expensive TDA would be from fossil fuel or fossil-based sources. So if you methylate terephthalic acid, which now costs €1,200 per ton, to the methyl ester and then convert it to TDA, you would end up roughly around €2,000 per ton. So you can already see that TDA from the waste sources is really cheaper than from fossil-based sources. And well, next to that, TDA cannot only be used for Twaron, but you can also imagine lots of other valuable applications that we are looking into further. I want to go back a little bit to the knife separation method, because you don't only end up with terephthalamide, of course, but you also have the polyolefins left. And as André showed before, you can use polyolefins in a pyrolysis setup to convert it to BTX, which we also did in collaboration with the university, in this case with Tim Engels, who was a PhD student in there. So you can see that using a similar setup as André showed before, we can convert the residual polyolefins into a nice selection of components, like where you end up with like 5.5 weight% BTX, but also you end up with some olefins, which is roughly 20%. So in the end, you can still obtain 25% of valuable materials out of the secondary waste stream that we produce from the ammonolysis. So if you combine all of that together, you can see that from PET waste, we do an ammonolysis, we end up with 64 weight% TDA. We produce a little bit of alkenes and BTX, and I did not show this before, but there's also some products that end up as solubles in the filtrate. But this also includes the ethylene glycol that you also free out of the PET waste stream. So to conclude a little bit, out of PET trace, the waste stream here, we can make valuable components that you can use in applications for, among others, Twaron. So as conclusions, take-home messages, plastic waste has more potential than just incineration or landfill. Even the most contaminated PET streams can be used to create strong fibers like Twaron. Secondly, plastic refinery in combination with smart sorting techniques has potential to fully valorize mixed plastic waste into valuable chemicals. And catalytic pyrolysis is an essential part of the refinery process to maximize its potential. Well, thank you for your attention, and I will give the floor back to the organizers. Oh yeah, stop sharing. Don't see my mouse here.
Sorry, I thought my microphone was on, only my camera. So thank you, André, and thank you, Jarno, for your presentation. And then I would now like to give the floor to Chenyu to tell us a bit more about AI enhanced prediction of plastic pyrolysis. And I see already some people are asking questions in the chat. Don't forget, because after Chenyu has finished the presentation, we have time for question and answers. So I'll give the floor to you, Chenyu.
Yes. Yes, good afternoon, everyone. My name is Chenyu, and I'm a researcher at MNEXT in Biobased Resources and Energy Group. So I'd like to present our recent work on AI-enhanced prediction of plastic pyrolysis. So let me first briefly show what is the pyrolysis. Pyrolysis is a thermal chemical conversion process where materials are heated in the absence of oxygen. So different feedstock can be used for pyrolysis, for example, biomass such plastic and tears. So unlike combustion, the material are not burned directly. Instead, the longer polymer chains are thermally decomposed into smaller molecules. So the main products are typically the combustionable gas, liquid oil, and solid char. And the liquid fraction is especially interesting because it can potentially be used as fuel or as a chemical feedstock. Now, imagine you are the manager of the pyrolysis plant, and you need to sign contracts with recycling companies for waste plastics. A company comes to you and say, "Hi, we have tons of waste plastics. Would you like to buy them? Which one would you like to buy?" So they have a PET, HDPE, PVC, LDPE, PVPS, and other plastic. So now the question comes to us: which plastic would you actually want? Because not all the plastic are your friends. Some plastic help you produce the valuable oil, and some plastic may produce the gas, or even worse, some produce chemicals that can make your reactor dead. Okay, and even if you already have the plastics, you still have another problem. How should you run the reactor? High temperature, low temperature, small particles, long residence time, more PS, less PP, more PE. So a pyrolysis reactor is a little bit like cooking. So if temperature is too low, nothing happens. If too high, everything turns into gas. So, but in practical experimentally testing, every possible condition is extremely expensive. So instead of sacrificing our engineers, workers, and students and reactors for years, I would prefer the machine learning stuff for this, because machine learning can help us find the good conditions much faster. So these slides show the main idea of this project. We start with 3 questions. First, which plastic compositions are good for pyrolysis? And second, under what conditions should pyrolysis be performed? And the third one is, can machine learning help us to predict the yields and find the optimal conditions? So the goal of this work is to use the machine learning to make pyrolysis more efficient and more predictable. So in this project, the methodology contains several steps. The first step is data collection. So in the first step, we collect the experiment data from literature by using AI agents to do the literature mining and screening. So finally, we collect 824 data sets from literature. And the input data includes weight percentage of 6 common plastic: HDPE, LDPE, PPPS, PVC, and PET, and also particle size, filling rates, and the reaction temperature. And the outputs are the yields of liquid oil, gas, and char. And the second step is to do the data pre-processing. So we use 2 methods to reconstruct the data size. For example, media imputation and the denoising auto encoder. And next, several machine learning models were developed and compared. So we tested 4 neural network-based models, which are XGBoost. It's like a decision tree model. And the MLP is a classical multi-layer neural network model. It's more like a black box model. And residue MLP, it's based on the MLP model, but introduce some escape connections, which can help to improve the training stability. And another one is named the CAN. CAN model is a new architecture designed to better learn the nonlinear functional relationships. It's more like health white box. It's trying to interpret the relationships between your inputs and output data. And next step is to do the evaluation. So we reserve the 20% of the data as the test data. And then we compare the R-squared mean absolute error and the root mean square error to see which model perform better. And the next step, we did the sensitivity analysis to identify which parameter most strongly influence liquid oil yield. And finally, we did a grid search to find the optimal operating window. Here are some preliminary results. So first, we compare the prediction performance of 4 different models for liquid yield. Among the test models, XGBoost achieved the best performance with an R-squared of 0.82 with the lowest MAE and RMSE. But also the residue MLP also performed reasonably well. So based on these 2 models, we performed the sensitivity analysis to understand which parameter strongly influence the predict liquid oil yield. So from the heat maps, we observe that PVC content, PS content, PET content, particle size, and temperature have the largest impact on the liquid yield. So this result indicates that both feed composition and process conditions play important roles in pyrolysis. Here we examine the influence of PET content on liquid oil yield. So the increased PET content significantly reduces the liquid oil yield. And this is consistent with chemistry of the PET pyrolysis because PET contains high oxygen content and its decomposition tends to produce more CO, CO2, and other oxygenated compounds. So as a result, less carbon is converted into hydrocarbon liquids, which leads to lower oil yield. We also test the influence of the PVC content from the model prediction, where the PVC also showed a negative impact on the oil yield. This trend is also consistent with the chemistry of the PVC pyrolysis. During pyrolysis, PVC undergoes dehydrochlorination and release hydrogen chloride. But hydrogen chloride can corrode equipment, poison catalyst, and disturb the radical reactions. These reactions will also shift the product distribution toward the gas and the solid residues rather than liquid oil. So therefore, we should, in practical plastic pyrolysis, PVC and PET are usually removed from the feedstock. We also test the influence of the PS contents. We can, from the figure of the influence of the PS contents, we can see the increase in PS content slightly increase the liquid oil yield. And PS favors oil production due to the depolymerization and form aromatic liquids during pyrolysis. But in practical, PS is often better processed separately to recover styrene monomer because the styrene monomer has a higher value. We also test the influence of the PP. So we can see from the figure, the liquid yield slightly decreased and the PP contents increased. So higher PP content promotes the formation of lighter hydrocarbon and gases. But so here we suggest a PP fraction below 28% can maintain the liquid oil yields above 80%. So that's our suggestion. So in conclusion, so PS is better to be processed separately, and BP we should keep the percentage below 20%. Also, we test the influence of particle size. The result shows 2.1 milliliter give the highest liquid oil yield. Smaller particles means more secondary cracking. That means more gas. And large particles, the heat transfer will be limited. And we also test the influence of the temperature. From the results, we can say 530 degrees give the highest liquid oil yield. Lower temperature, incomplete, that means incomplete polymer decomposition. The high temperature, that means more secondary cracking and more gas. So there is a balance between primary decomposition and secondary reactions. So in the final step, we first define a realistic parameter range and then perform the grid search within this range to reduce the computation time and cost. So based on the grid search, the model predicts an optimal operating window for maximizing the liquid oil yield. So the results suggest that PVC and PET should be avoided, and PS is around 30%, but this number is the maximum value within our defined range, because PS tend to promote higher liquid oil yields, as what I mentioned before. But in practical, PS is often better processed separately. For PP, keeping the content below 20% helps maintain the higher liquid recovery. And the HDP and LDP ratio is 1:6 is optimal. For PP, keep for the particle size and temperature 2.1 milliliters and 530 Celsius degree. So under these conditions, the predicted oil yield reach about 83%. The take-home message. So in this research, we developed a machine learning framework to predict a liquid oil yield from mixed plastic pyrolysis. Extribals show the best performance, while residual MLP also performs well, and it can improve the neural network stability under these limited data conditions. And we did several sensitivity analysis. It shows PS promotes liquid oil formation, but PVC and PVT significantly reduce the oil yield. And finally, through the grid search, we finally find optimal operating window. So that is my presentation. Thank you for your attention. So I will give back to the main stage.
Thank you very much, Chenyu. I would kindly ask the speakers to put on their camera and their microphone, so they're also able to answer the questions that are put in the chat. And I saw there's quite some questions for you, Jarno, but I'll first ask a question to Chenyu because it's still fresh what you told us. Can you tell me a bit more? What are the main limitations and future directions of your approach, and how do you plan to further develop your model that you have created so far?
Yeah, okay, that's a really good question. So currently, the main limitation in the dataset itself. So although in this project we already collect more than 800 data points, but you know the literature data are still quite different. So different studies use different reactors, scales, and even different analytical methods. So it's difficult to keep the KPU data consistent. And also another limitation of this work is the model, the machine learning model only can capture the correlations between your input and output data, but it's difficult to interpret the reaction mechanism besides. So it's quite, it's just a tool to predict your model, but it cannot difficult to explain your backside mechanism. So that's one limitation.
Mm-hmm.
And for the future direction to develop this model, so the first is to improve the data quality, because now 800 is not enough. For if you want to train a better performance model, it's better to like 10,000, 10K of your data sets is a reasonable value. Yes. And second direction, I'm also interested in include another additional outputs such as oil composition or gas composition rather than only the overall yields. And also like what the first two speakers said, the catalyst also can be used in pyrolysis. We also would like to include this data for the input data. So eventually, the final goal is to develop a more practical decision support tool for reactor design and process optimization. That's the general idea of the future work.
Okay, and then when would you be, how do you say, confident enough to sell your idea to a company so they can actually predict?
I would like to say, yes. So first, if the data size, if the data quality can be improved a lot, I will have more confidence to persuade them to buy my idea.
Okay.
Yeah.
And let me go to Jarno now, because well, you sold Chenyu, you should have Notepad in your composition actually to get a good result. So well, then I think Jarno was already smiling, but I didn't see you at that time. So there are quite some questions about your presentation, Jarno. I'll just go through them. Maybe you already read them in the chat yourself as well. First question was from Chen. Could you explain how the composition of the PET trays was determined?
Yeah, we determined that at NTCP, is the waste company in Heerenveen that we collaborate with, and they, well, object-based composition you just do by hand and look at what's in there, and then weigh how much everything is. But the polymer-based composition, we use that using a flake analyzer. Basically what you do is you put the flakes through little by little, and then it goes through a screening with FTIR and NIR, and then the computer uses based on with an AI based on trained on a database. You basically compare what's in there and determine the weight of everything in there.
Okay. And well, let me see. Well, Chen, you already mentioned in looking at the catalyst. I also see a question about the catalyst. Jarno, did you look into the replacement of the current catalyst that you are using? And if so, which other options did you look into?
The catalyst for which reaction? Chlorine?
Chlorine, yeah.
We did not really look into different well, a catalyst for the Hoffman rearrangement, no. But we look at more into ways on how we can chlorinate the terephthalamide, and then we saw that the chlorine gas works the best for us. But you could imagine you could also use bromine or another leaving group.
Yeah. Okay. And I see a question from Janneke, but I think she's sitting next to you.
Yeah,
so maybe Janneke can ask the question herself.
Yeah, I will. So we are all in the same room.
Yeah, I could hear that.
Yeah, well, since we are from the Lectorenplatform Biobased Economy, so that's I think it's an obvious question. But I think that production of twaddle from pet waste. It's a very nice example of chemical upcycling.
Mhm.
But are there any options for truly bio-based twaddle? So that's my question, because pet waste is mainly fossil-based as well, right? So so that's what are the options? Do you think that there are options, and if any, do you have any guesses?
Well, I would agree that PET waste is mainly fossil-based, unless you make PET out of biosources, of course. Then. But I think we also looked into making Twaron out of biological materials. But André would know more about that.
No, I showed it in my presentation. Yeah? So we used crude glycerol as a source in order to make twaron. It had the same quality as fossil-based twaron. So that is yeah. So most of these drop-in chemicals can be most often be prepared from biomass or end-of-life plastics, depending of course on
wonderful.
Yeah.
Okay, that was my question.
Good.
Almost an internal discussion.
I also see a question from Rob. He asked what's the amount of energy needed for the process, especially comparing to fossil produced twaron.
Well, I don't know that from by head, but I know Pascal and Jos back in the day did calculate that based on the system they developed, and well, also the reaction that you need for that. I can say like one nice thing about the ammonolysis is that dissolving ammonia in ethylene glycol is an exothermic process, so you can use the heat of that also to heat up the reaction itself.
Okay. And then there's a question from Chen. So would your process also be suitable for treating PET blends textiles?
Well, PET blend textiles as in PET cellulose textiles. We tried also in our reactor. However, what you see then, if you have like a textile fabric, it mostly wraps around the stirrer. So that was not that ideal. So it just mostly encapsulates everything and did not really break down. But we were still thinking of blending the textiles further into smaller pieces and see if you could ammonolyze that. But we have not tried that.
Yeah. Okay. And I was also wondering, because you told, well, you looked into twaron now, but you also mentioned very briefly that you also are looking into other, that's also useful for other applications, your base product. So can you tell us a bit more about that, or is that still a secret?
Well, I think I can tell a little bit. What we're trying at the moment is to make from the TDA to make urethanes out of it. So you basically, if you do the Hoffman with an alcohol instead of water, then you'll end up with carbamate, and you could have like more applications of that.
Thanks. I also see, I think that's a question for you, Chenyu, a question from Karen. She asked if it's a problem that PET and PVC have a negative effect on the oil yield.
Yes, it is. It's a significant problem for pyrolysis processing. Yeah, so in our results, PET and PVC both show the clear negative effect on liquid oil yield, because for PET it tends to form more gases and oxygenate compounds instead of hydrocarbons. And PVC also reduce the liquid yields, and more importantly, it can significantly decrease the oil quality due to the hydrogen chloride formation, and it can produce some chlorine-containing compounds. So these compounds can corrode your equipment and poison catalysts, and make downstream operating more difficult. The PET also can decrease the oil quality. So that's definitely a big problem.
Okay. Does that answer your question, Karen?
Yeah, partly. I was more thinking about the fact that actually PET and PVC is a really big stream on plastic waste. So I was looking into thinking in that direction.
Mm-hmm. So you mean the PEC and PVC can decrease the liquid oil or something else?
Yeah, so I agree with your concerns. So the problems encountering the pyrolysis of PET and PVC. But if you look at the volumes, I think they are the main streams of plastic wastes.
Yes. But I think it's more about the during the sorting process. So it's better to use more sorting technologies like infrared technology to separate the PVC first. Otherwise, our liquid oil can be reduced and the quality is not good. So it's more like in sorting technology. we need to, yes.
Yeah.
So you would say for the PET and the PVC, you use a different technology than what you are looking into.
Yeah, for PET, I think maybe for the first two speakers, strategy could be promising, and also maybe could use a traditional mechanical recycling or something different pre-treatment steps. Yeah.
I see you have a question, Chen. Can you ask yourself? Apparently not.
Well, I am fast. No, I mean, like Andrew, you're doing this bio-PTX process, right? You want to produce aromatics. I think the PT is one of your feedstocks. Is that correct or not?
Yeah, PET, the drawback is, of course, that it also contains a lot of oxygen. Yeah? So the yield based on carbon is lower than for polyolefins, and also you have some side reactions. But to go back to the question of Karen, so indeed, yeah, so as companies like NTCP are able to separate these mixed plastic streams into a PET-rich stream and a PET-low stream. So in this case, the PET-rich streams can, for example, be used in the process which Jarno has described, and the PET-low stream can be used for pyrolysis. So, like you mentioned, Chenyu, using proper sorting techniques, then you can easily prepare different feedstocks which are suitable for pyrolysis, or, for example, the upcycling concept, which was being shown by Jarno. So it's often a mixture between sorting collection and getting the right feedstock for your follow-up, your downstream processing.
But PVC, I think, is still a problem.
Yeah, avoid as possible, because that's really corrosive and destroying your apparatus. So that I fully agree. Yes.
Yeah. So we have a solution for PET, and we have a solution for a lot of other plastics, not for PVC yet.
No. No.
Yeah. Okay. Are there any, well, the questions from the chat are left. I think it's a nice ending also, that we need each other in this case. So it's a good way to know that first we need mechanical, or at least we need separation, and then we can choose different technologies to treat our plastics. And I think today we saw some nice examples of that. So I would like to thank everyone for attending this webinar, and again, André and Jarno and Chenyu for your very nice presentations. And again, we will make sure that the presentations are available, sent to you later on. And if you have any questions, feel free to contact the different speakers of today. So thank you very much. I hope you have a warm and not a rainy evening today. And I hope to see you next time with another webinar of the Lectorenplatform Biobased Economy. So thanks very much.